So if we have iron H2O whole 5 OH 2 positive. So in this particular case, we saw that lattice contribution is existing, balance is existing. Here lattice contribution is not there. Lattice contribution is there, balance is not there. So what do you feel that which one is going to have more electric field gradient, and corresponding which one is going to have more separation between the two peaks? That means quadrupole splitting. Is it A or is it B?
A is more quadrupole split.
So A is having more electric field gradient, and therefore there would be more splitting in your A case. That is why in the graph you can see there are two types of fields. First one is having more splitting compared to the other one. The greens one are having less separation, whereas the red ones are having more separation. So the red one is belonging to your iron Fe2 wala system, and this one belongs to iron 3. Also, we confirmed it from the delta value, where you can see the delta dash is for iron 3. The green ones is having more delta value if you take the average of the two peaks. So this one corresponds to the iron 3 and this one corresponds to the iron 2. That is way when we are just doing the gamma radiolysis of your iron aqueous solution, how the spectra tells you like what kind of interactions and what metal oxidation state is going to be there in your solution, which you can't see actually visualize by your normal system. So Mossberg spectra plays a very important role to define each and everything, like coordination also it will expect, and it will give you proper splitting and decide like what is happening inside the system. So is this clear? Then we can move on to third example.
Okay, ma'am, clear.
Now we have another concept of ligand exchange reaction. So this is the sixth part that we are talking about. So ligand exchange reaction, if suppose I am having metal and here is one type of ligand, now I'm replacing it with L dash. So it would be either a combination of L dash, or it could be completely L dash ligands. So that is the ligand exchange reaction happens. So firstly, what we are doing, we are having again the iron sulfate 7H2O. When we dissolve it in water, it is having this kind of coordination complex, iron water plus. And now what we are doing, we are adding 6 equivalents of your Cn negative. Now what will happen to that and how your Mossbar spectra is going to look like. Right? So when we saw this reaction was then performed at 5 degrees Celsius, because we have to check the Mossbar spectra and how the spectra was looking. So we'll just draw the spectra over here. Firstly, I'll draw one thing. So here we have a small doublet here also appears, and then it starts increasing. And also there is one more peak singlet comes over here, and then it is having more shape. So then less in concentration now, and ultimately we only have green one. So we are having three types of now peaks. The red ones, which is a doublet. That means one peak got split into two. Then we have another set, which is this blue. That is also doublet. But as you can see, it is having more delta dash compared to the red one, but less delta EQ. This is more, that is less. And the third one that we are having is green spectrum. That is singlet. It's having delta double dash. That means the isomeric factor is even more increased than the blue line. And delta EQ is 0 because there is no splitting of the peak. Now we need to find out what is red, what is blue, and what is green over there. So just looking at the spectra, is that clear? Like, how do we come to know like what is red, what is blue, how the delta value is more and delta EQ is less, and what about the green? Or is there any confusion? Because first you have to define the spectra, then we can start thinking about the reaction, and then we come to the conclusion. Iron is existing in what coordination number, what kind of ligands are attached to it, and what is the oxidation state of iron. So is there any question? Here we are actually talking about the ligand exchange reaction, where we are taking an iron sulfate solution in water, and then we are putting cyanide over there. Cyanide ka source is potassium cyanide we have taken, and where we are adding 6 equivalents of the cyanide. We expect that cyanide will replace your water. Why? Because cyanides are more stronger ligand compared to the water, so that displacement reaction can happen very easily. So when you know that it is changing the weak field ligand to strong field, there would be variation in the oxidation state. There would be possibility of variation in your like pairing of your spins, like whether it would be high spin, whether it would be low spin, whether it's a combination of both. So depending upon that, that's why we are able to see here with the passage of time how different spectras are coming. So say for example, if it is 0 at 0 minutes, that means the reaction has not initiated. One kind of spectra. After 160 minutes, it was looking like this way. Then after 720 minutes, it was looking like this way. Then after 1500 minutes, then ultimately after 6000 minutes, we got only one peak singlet over there in the spectrum. So is this clear that how we define different kinds of cases over here? Or is there any confusion?
No confusion, ma'am.
So what we actually started, so we need to see, we have iron, water, as I said, we are starting with this particular +2. So I'll draw it in red only. Okay, so we are starting with this A. Now we said we have Cn negative. Firstly, one Cn, it is going to form this kind of structure. That 5 of the Cn is going to be replacing the water molecule, and it comes as, it stays in iron +2 only because there is no reducing or oxidizing agent we are using, and ultimately it would be Cn6 4 negative, which is also +2, right? So now here we have during the process, because we have in the spectra 3 kinds of traces: red trace, blue trace, and green trace. If exactly at low temperature, if we would have done the thermostat spectra at room temperature, that means at higher temperature, then isolating this particular spectra won't be possible, because at that time the conversion of this particular species to the CN6, it is very easy. That means all the water molecules have been replaced by CN. But since we were doing at low temperature, 5 degrees only, so we could isolate all the A, B, and C. That's why in the spectra, we could able to have the red trace, blue trace, and green trace. Is this clear? Is this point clear? That what temperature role why temperature role is important?
Ma'am, at low temperature, this type of spectrum will come up.
I didn't hear you. Sorry.
Ma'am, at low temperature only, this type of spectrum will come or not?
Yeah. So in these, when low temperature is there, that means you can analyze your spectra. There is time to have that conversion to happen. Otherwise, that say for example, if I have two molecules, I'm giving too much of energy, so immediately the transition will happen. Like one goes to their displacement. Like if the movement is very fast, you cannot see anything. Like how should I say? If this one point is there, like my right hand finger and the left hand finger, so if I'm rotating it very fast, so you could not be able to identify which part is what, right? So the transition or the movement is so fast that we could not identify which hand is what. For example, here, when we are having, you might have heard about this fluxional behavior. So if we have this cyclohexyl group, there would be two types of protons are there. One is axial, one is equatorial. So if we record NMR at room temperature, both will give you one peak only. But if you're recording at low temperature, this will occur as different, this will occur as different. So we get two types of peaks. Similarly, if we have low temperature, we can see actually the exchange is happening and the complexes could be identified. But if it is happening at a very high temperature, the complex change or the ligand exchange is so fast that we can't even identify. It will start with this A and it will end up with this one. We can't see intermediate. So yeah, at low temperature, we earlier to low temperature only, we can see these kind of transitions which are happening.
Okay, ma'am, I understood.
Yeah. So now we have A, B, and C. Now we have to assign which one is red trace, which one is blue trace, and which one is green trace. So can you please try on your notebook? If you can let me know like which one of these is red, blue, and green, then we will solve it. So this is the spectra which I've kept for you. Now just try to solve it by your own, like which one is A, which one is B, which one is C. I'll just write here also. We are saying A is iron H2O whole 6, 2 positive. B is iron H2O, CN5, 3 negative, and iron CN6, 4 negative. So you need to tell me which one is red, which one is blue, and which one is green. So can you please try? If you understand this concept, then it is very easy to answer any question for you.
Okay, ma'am. Ma'am, A complex for red, ma'am.
Yeah, okay, great.
Then C complex blue.
C or B?
B complex blue. C complex green.
Right. So how did you come to this? So now we will, so it is absolutely correct that A is red, B is blue, and C1 is green. So now we will look into proper description of it. So you just let me know if we are going in the right direction or not. Okay. So firstly, we'll take up iron H2O whole 6 positive. It is again the same thing. We know that what it is a H2O is a weak field ligand. So iron 2 plus it's high spin, and therefore it is D6 high spin. And we know in D6 high spin, it goes like, because of the Jandler distortion also and balance contribution also, it is having EFG. So EFG is there because both the factors are there. And also in iron plus 2, we expect one kind of delta value. We have set it delta. Now taking the second condition, B, iron, water, and CN5. Now, if we have this kind of condition, here, iron in plus 2, it's D6. Now, we have to see, in this particular case, the EF, the delta EQ has been reduced compared to this delta EQ. Okay? So, this is going to make a low spin. Why I'm saying low spin? If I'm not having a low spin over there, if I'm having low spin, then valence contribution is 0. There would be lattice contribution or not?
Lattice contribution. Lattice contribution is not available.
Sorry.
Lattice contribution available, ma'am.
So lattice contribution is there, valence is not there. That's why the delta EQ is less. I am just saying it as B for this B complex is less than delta EQ of A. Because here both the lattice and valence are contributing. That's why EFG is very high and delta EQ is high. Whereas in this case, LC is there because of two different ligands are there. Valence contribution is not there. So can you please tell me why here D6 is getting low spin and not high spin?
What, ma'am?
Why I'm saying that this particular complex is a low spin complex and not high spin complex?
Because distributions of d electrons, that is the difference between them.
No, say for example, if I was having this A, iron H2 whole 6, so I put this electrons in a high spin manner, but similarly iron in +2 in this complex, I put it as low spin. What is the reason behind giving it as a low spin and that is as a high spin? So high spin, low spin, we define it by what? Is it the
Low,
is it
low
the
spin means that the ligand, the strong ligand.
Yeah.
High spin means that is weak ligand.
Right. So here, if you will see, out of 6 ligands, one is the weaker one. The 5 ones, the other 5s are very strong ligands. So strong ligands become very dominant in nature. That's why the electrons, they got paired up and therefore it makes a low spin complex. Okay. Now the third one, we have all the ligands have been replaced by the strong ligands and it is making still iron in +2. So here we have iron in +2, D6, low spin. Now you tell me lattice contribution and valence contribution.
Lattice contribution not available, ma'am.
Right, okay.
Valency contribution also not available.
So that's why we only saw singlet. One peak was there was no splitting. When these factors are not there, that means EFG is not 0. Sorry, EFG is 0 and delta EQ is also 0. That's why this one is red trace, this is blue, and this is green, which is clear from the spectra. The red ones is having more delta EQ, right? And if you will see carefully, so tell me one more thing, that it is having delta double dash, this was having delta dash, and this is having delta. And I said for A complex, B, C, delta, delta dash, delta double dash, this is mode negative. So iron water, iron 1 water and 5 CN, and iron 6 CN. So can you please explain? Splitting we saw, but what about their isomeric shift values? Why this complex C is having more negative delta value compared to the B and A?
And once again, tell your question now.
So here we saw splitting pattern we saw from the electric field gradient, and electric field gradient parameter comes from lattice and valence contribution. That we just explained from these particular things. That is clear. We got to know red is what, blue is what, and C is what. Now, if you'll see in their spectra also, the red one ka isomeric shift, if I'll calculate the average value, this is delta. Blue one is having little more negative delta value, which I have defined as delta dash, and the delta double dash is even more negative. So I want to know why delta double dash is more negative compared to delta dash and then compared to delta, considering these three complexes. So delta value depends upon which two major factors?
Yes, ma'am. The C complex are having more negatives
Hmm.
because both lattice contribution and valency contribution is not available compared than other two complexes.
That valence contribution and lattice contribution only affects the splitting, not the delta value.
Okay, okay, ma'am.
So the isomeric shift that we read it in, I think, after 8th lecture or something, what are the two major factors on which the delta value depends? As we said, na, ki delta EQ depends upon lattice contribution and valence contribution, which will tell you about the splitting. That is one thing. Delta value depends upon what? Say, for example, when I ask you RnF2 and RnF3, which one is going to have more negative delta value?
Fe3 plus
How do you say that?
because it's having a more oxidation state,
Yeah.
so it's
So-
have
Right. So either we have to talk about oxidation state, keeping the spin complexes say constant, or we talk about the spin of that. Like oxidation state is constant, whether it is making high spin complexes or low spin complexes. And we came to the conclusion, if we have higher oxidation state, there would be more negative delta value, or if the oxidation state is constant, and if we have low spin complexes, which will take up the more electrons, and therefore that would be having more negative delta. So now I have given you the hints over here that these are the two factors on which delta value depends. Now explain the reason why complex C is having more negative delta value. Okay, first tell me, in all the three cases, what is the oxidation state of iron?
the first A complex 2 oxidation state Fe plus 2, ma'am.
B
Next one that also plus 2 oxidation state.
T.
C complex also plus 2 oxidation state.
So that means this factor we can't consider because the oxidation state is constant in all the cases. Now think about the
Yes,
other
ma'am.
factor. This one is
Jahn-Teller distortion.
Jahn-Teller distortion only affects your delta EQ, not your delta isomeric shift. I'm talking about this high spin and low spin. So you tell me whether this complex is high spin or low spin.
The A complex is high spin complex, ma'am.
Second one,
Second one low spin complex.
this one.
That also low spin complex.
But among these two, what do you think? Like which one is going to have more less shielding effect on the s electrons? Here there are 5 strong ligands. Here there are 6 strong ligands. Which one is going to have less shielding effect?
C complex is less shielding.
So it would be having the least. Just a second. So this one is going to have least shielding effect because it is having more number of strong field ligands. So now you tell me, if a complex is high spin, so what do you think delta value has to be more negative or more positive?
More positive.
Yeah. So it would be more positive. What about if I'm having this low spin, but this is having more strong field ligands? Which one is going to have more negative delta value?
C complex.
Which complex?
C complex.
Right. So because of more strong field ligands, it would be more negative. That is why C complex is having more negative delta value compared to the B and compared to delta A. So whenever it comes to isomeric shift, two factors you have to keep in mind. So we'll just have a summary of these two main things. So whenever we will be talking about isomeric shift, we only have to consider two factors. One is check the oxidation state, keeping that high spin or low spin complex is constant. This should be same. So you just have to see the oxidation state or d electrons. And if the oxidation state is constant, then check if oxidation state is constant, then check whether strong field ligand or weak field ligand are there. That means, is it making high spin, low spin, or high spin? If it is low spin, that means it will be having more negative delta. If it is high spin, it will be having less negative delta. More oxidation state, that means more delta negative. Less oxidation state, less negative delta. So this summary you have to keep it in mind. And the other factor is the quadrupole splitting. That splitting that I am continuously we are seeing in the spectra, that how the splitting between the two peaks occurs. This splitting occurs. Earlier it was only one peak, then it splits into two. That depends upon lattice contribution, which comes from if we have different ligands or we have Jahn-Taylor distortion, and valence contribution comes from unsymmetrical filling of the electrons. You have to keep these factors separately when I'm talking about isomeric shift and when I'm talking about the quadrupole splitting. You cannot mix these factors into the isomeric shift, then otherwise you will get the wrong answers. So is it clear?
Clear, ma'am.
So therefore, when we have, if we'll see the relative abundance, when ligand exchange happens. So firstly, the graph goes like this way. So this one is for your iron, water 6. What it says that it was earlier 100%, then it come to 0. So this is 0. So relative abundance, that means its concentration. Then second one, we were having that iron water wala. So this is also this one also goes from 0, goes to the maximum, and then again come back to 0. And the third one that we have is goes from 0 and then becomes the maximum, which is the final state. And this one is your iron 2 CN6 4 negative. So this is what we have, the relative abundance whenever ligand exchange happens. So is the graph is clear? Like how we are defining which one is going. These kind of graphs can come directly to your paper where they can ask, identify which trace is for which complex. So you need to understand the reaction kinetics, check the Mossbauer spectra, and then come to the conclusion which one is going from 100 to 0, like starting with there was 100% and then it got vanished. Second, which one is the intermediate that goes from 0 becomes maximum and then comes back to the 0. And the third one, which was not there earlier, and ultimately the final product is your this one, and it will go from 0 to 100%. So clear?
Clear, ma'am.
Now, another more important example is ferrocene kind of systems. So ferrocene, they are sandwich complexes. So here we have ferrocene is nothing but FeCp2, where what is Cp? I'll just show you over here. So this is cyclopentadiene. So this is a kind of system where it is C5, 1, 2, 3, 4, 5, and 6. These are hydrogens. So this is C5H6, which is called as cyclo. Penta means 5 carbon. Because of these two alkene double bonds are there, so this is diene. When a base comes, it will take up one proton and that will give a negative charge. So it will be now negative here, dienes are here. So this structure, when we have a negative over here, so if you will count the pi electrons, this becomes 6 electrons. Why? Because now it will participate in resonance. So it will be like movement and delocalization is happening. So it would be double bond here. Then we are having it here and on this arrow, this negative, this is double bond, this is double bond. And ultimately we have a hybrid resonance hybrid structure where the negative charge is all around the ring, and that is called as cyclopentadiene. So this particular Cp, this is called as Cp, which gives you one negative charge. This is an electron donating ligand, very strong ligand. So this is how it combines with Rn to make a complex. So we basically have this kind of we have when we have this Cp and when we are using KOH, a base, it will form this cyclopentadienyl ligand Cp negative, and when we are treating it with iron plus 2 salt, it will form iron Cp whole twice, right? So this complex particularly, it's an electron transfer agent. Second, in organic solvents, it does not react and it acts as a internal source control for varying the potential, applied potential. Monitoring के लिए we use this kind of particular agent. So they would be having a CV pattern. That electrochemistry में you will see a kind of this kind of duck shape where it would be showing you iron 2 to 3 transition, so that peak remains constant with a certain distance with a potential, redox potential. And with respect to this particular curve, we see a lot of, we can actually calibrate our different systems. So we get to know about the redox potential. So we'll not go to that electrochemistry side. Our main focus is on the iron Cp2. So how the MOSFET spectra looks like for the iron Cp2. So here we need to understand firstly, in iron Cp2, we have read it in the group theory. There are two possibilities. Firstly, we have, this is an eclipsed form where both the rings are at 0 phase to each other, and the other form is, this is your staggered form where 180 degrees are there. So actually there are the orbitals which involves. So firstly, you tell me, do you remember that what is the point group of these two particular complexes?
D5H group.
Yeah. So firstly, how do we check that, whether it is linear, whether it is cubic or something like that? So firstly, it is linear molecule, in linear point group, no. Is it cubic? That means belonging to tetrahedral or octahedral? No. Then we need to see whether CN exists. Like what is the principal rotation axis existing? So as you can see, if we pass C5 from the center of these two rings and we are passing through the iron, C5 is existing and there would be a pentagon. That means 72 degrees rotation would happen. So C5 is existing. Then we need to see whether 5 C2s are there perpendicular to C5. Yes, it is present over here. Then we need to check whether the molecular plane is there. If we cut the molecule into two halves and the plane is just perpendicular, the C5 is this one and plane is this one, which is perpendicular. That is called a molecular plane and that is existing, which will exactly reflect your one ring over the other. So when C5 is there, 5 C2 is there, sigma H is there. So this eclipsed one is having D5H. Similarly, staggered one would be having D5D because instead of the sigma H, it is having sigma D, which are bisecting the two C2s. So when we have D5H and D5D, we know that their point groups and symmetries are different. Normally, staggered one is the more stable form of your ferrocene. Why is it so? Because here, if you will see, they're the orbitals. If they are at the same positions and facing towards each other, there would be more repulsion, whereas there it's the less repulsion over in the staggered form. So it becomes a more stable form. Now, how this looks like? We have also one more form. If I will substitute this CP with this CP, where I'm having methyl groups instead of the hydrogens. So this is called as CP star. This is CP. Okay. So now if I have iron CP2, iron 1 CP and 1 CP star, this is also one electron charged ligand and this is CP star 2. So we need to find out which one is going to have what kind of MOSFET spectrum. So firstly, we will see the iron in +2. Since it is a different kind of geometry, it is not octahedral, so we can't split it into an octahedral field. So here the iron in +2 having these 6 electrons. So the energy would be, so this is E1G, this is A1G dash, this is E2G, where it is formed as X square, Y square, and XY. This one is DZ square, this one is DXC, DYZ. So this kind of splitting happens when we have these kind of systems. And since we have 6 electrons, so it goes like this way. So this is the filling of your iron CP star. So if you will see here in iron CP2, this particular thing, you need to remember how the filling is happening. And if I'll ask you, lattice contribution is there, or if I'll just generally ask that whether EFG is existing in this case or not.
Yeah, the EFG is not available, ma'am.
Okay. So normally when we see this case in T2G, EG or something like that, here when we talk about dx square, y square, dz square, dxy, dyz and dzx, we generally say it is unsymmetrically filled in all the 3 directions, x, y and z, right? And if I have 1 electron over there, then we call it as unsymmetrical filling because the axes are having different electron density. Even though they are paired, we need to see that splitting has happened. The energy levels are not same. And because of that, the X, Y, Z direction, the electron density is not symmetrical. That is unsymmetrical. So if it would be like this particular way, okay, this is filled properly. This is called as symmetrical filling. This is not called as symmetrical filling. It is still unsymmetrical. If you see x cube, y squared, xy, it is having more electron density compared to the z direction. So that is not symmetrical. For symmetrical thing, it has to be equal distribution of the electron density along 3 axes. That's why, because of unsymmetrical filling,